thanks for the invitation. It's a great honor to give a course in this prestigious institution, École Normale Supérieure de Paris. So here is the outline of my talk. So we have the two hours. The first hour will be devoted to quantum cryptography. We will recall what is the RSA public key system that everybody is using for commercial transaction on the web. And then I will try to start quantum mechanics from scratch, but not completely from scratch. I will use, in fact, as a key example to understand the quantum rules, the famous LKB photon box of the Serge Haroche group, okay, to explain the different rules that are used, in fact, in quantum cryptography and quantum computation. Then I will present the BB84 quantum key distribution protocol, which is, in fact, very easy to understand in a certain sense. I will try to explain the structure, not the complete, in fact, the factorization algorithm of Shor, because it is impossible to do that in 1 hour, but to explain here what is a quantum gate and what is a quantum circuit performing a kind of huge unitary evolution, okay? And this will be, in fact, the quantum Fourier transform because the computations are quite easy. So, and the second part of the talk will be on quantum error correction and the feedback issue. Okay, let's start with the RSA public key system, okay? So it is something that goes back to the last century, and the protocol is based, in fact, of the difficulty of factorization of large numbers, which are the product of two large prime numbers. So here you have the size, the number of bits of such a RSA number, okay? And the protocol, I recall here the protocol in 3 steps, okay? So it's something that usually people knows when I have done a little bit of arithmetic and cryptography. So what is public? It is the RSA number and an exponent. And what is the secret key is another exponent. And the trick is just this. You take your message M that you want to send. To encode the message, you elevate it at the power of modulo n. And to decrypt it, you take ME, which is A, and you evaluate it at power, in fact, D. So this is A. So this is encryption, this is decryption. So something which is very basic. And the trick is that this guy is secret. So when Alice, for example, wants to send its credit card number to Bob, which is here, she starts to do this first exponentiation, send A, the results of the exponentiation of M, and then Bob, just as he has to do, is to take this exponentiation, and he knows that it is, in fact, M. So it's just 2 exponentiations. It's a very simple protocol. If you have fast algorithm, in fact, to make exponentiation, which is the case. And the case, why is it fast algorithm? Because you use what is called exponentiation by squaring, where you have at least the number of bits, okay, of the exponent, just this. And this is a multiplication modulo n. Okay, so it is written here, so it is simple things. And it is based on quite very standard results in elementary number theory, okay? Okay. So it is something which is widely used. So what is interesting here, if you assume that Oscar, so here Oscar, what he knows, Oscar? He knows A, N, and E. And he has to solve A is equal to X, E, modulo N, with X. If he solves this, okay, he knows that X is the credit card. Maybe I will use this one. Yeah. Okay? And people specialists guess that there is no simple algorithm, which means with a number which is, in fact, a power of the size you need to store n, okay, polynomial power, such that, in fact, you can, in fact, solve this equation here. So this is the first point. So this is based on the RSA problem. And the RSA problem, if you know the factorization of n, then you can solve easily the RSA problem, because in this case, you just have, in fact, to inverse d modulo this guy, and it is OK. So the fact that knowing the factorization of n shows that you can compute easily the secret power d, and then you have this. And what is quite interesting to see is that this, the security here, is just based, in fact, on a conjecture. But there does not exist simple algorithm to factorize a number. Nobody has proved that. And what is interesting, so to motivate, in fact, quantum information and all this stuff, is that first, with this protocol that I will describe in few minutes, you have unsecure and unconditional secure key distribution, which is based, in fact, on the law of quantum mechanics. So it is not based on a finite power, in fact, computational power for the SPI Oscar. And the second point is that you have, so it was shown by Shor, a factorization of n in a polynomial time. So which means it is a sort of random process, which means you have an algorithm, you take n, and what you have with this algorithm is that you start the algorithm, and with a probability which is not zero, okay, which is greater than a certain bounds, independent of the size of n, the algorithm gives you, after this, in fact, number of operation, okay, quantum operation, gives you a prime non-trivial factor of n. So, and if you look at what is the size, in fact, the number of qubits that you need, in fact, to implement this algorithm, it is, in fact, 3 times the size, the number of bits of n, the number that you want to factorize. Okay. So it is clearly very interesting. But the problem is how to have a quantum computer, for example, for typical RSA number, okay, with this number of logical qubits, it's not simple. Okay, just to have this order in mind. Well, so to understand these two things, okay, we have to understand the quantum rules, okay? And if you want to understand the quantum rule from scratch, maybe you can use, in fact, this experiment. So it is an experiment that has been conducted here, okay, around 10 years ago. So in the group of Serge Haroche, and it was, in fact, this experiment was the third experimental realization of a quantum states feedback. And I have a small movie here to explain the experiment. You will see. And we explain this, and then we will do some computation with this. So what we want, in fact, to control is the photons that are trapped between these two mirrors. Okay? And to estimate the number of photons between these two mirrors, what you can do is to send probe atoms, which are this, in fact, pink torus, around every millisecond, around, this is the sampling rate. So you send, in fact, the SPI atoms here. They are prepared in a certain way. They interact with the photons. They are, after their interaction, they are post-manipulated, and then they are detected. And here it is the feedback scheme. So all this evolution, okay, until the detection is governed by the Schrodinger equation, okay, the usual Schrodinger equation. And as soon as you have a detection here, which is assumed to be instantaneous, you are here in the classical world, okay? So this is a classical signal telling you if the atom is in ground or excited state. And here you have a classical microwave pulse. I will just, in fact, what is the most interesting part I think for this experiment, it is in fact the quantum evolution until the measurement. Okay? The feedback scheme, I will not speak of that. Okay? And it is a particularly beautiful experiment to understand the quantum rules. Okay? So I will just concentrate on what is going on. What are the simplest model that you can imagine to represent this system? Okay? So what do you need to know? You need to know this thing. First, you have to combine three things, only three things, and it's enough. The Schrodinger evolution. This is the Schrodinger equation. And what is the Schrodinger equation? You take a unitary vector, the wave function, and it is just a rotation of this unitary vector. Okay? And in a certain sense, h is the rotation rate. Okay? It is just this. The second point is, in fact, the collapse of the wave packet, which is attached to the measurement process, which is assumed to be instantaneous. So you are in the Hilbert space H. You take an Hermitian operator O for observable. And here you have its spectral decomposition. So lambda mu is an eigenvalue. And P mu is the orthogonal projector on the eigenspace attached to lambda mu. Okay? And then when I measure O, what I get as measurement outcome, I get, in fact, a classical information, which is mu. With this probability, okay? It is just this thing. If I am in 3 dimensions, if I have P1 with lambda 1, and here I have P2 with lambda 2, I take my wave function psi, I take its orthogonal projection, okay? On here I have P1 of psi, here I have P2 of psi, it is nothing else. And when I measure, I have always either this guy or this guy. The length, the square length of this guy is the probability to be projected on the first eigenspace. The length of this guy square is the probability to be projected on the vertical axis here. Okay? And just after the measurement, what you have to renormalize these two vectors which have been reduced, whose length has been reduced. It is just this. So this is something which is completely non-classical, this. And the last part is the fact that, in general, you have a composite system. And for a composite system, each system at its own eigenspace. Here it is the system S, the photon, and Ebb it is the matter. Okay? So the probe atoms. It is a tensor product, which means that the dimension do not add, but multiplied. And this changed completely the rule of the game. And typically, this is the new Hilbert space. The Hamiltonian evolution, of course, it is the Hamiltonian evolution of a system, which means that you have an Hamiltonian, an operator on HS, tensor identity on the system. For the evolution of a matter, you have the identity on the system tensor, an Hamiltonian for the matter, and you have here an interaction Hamiltonian, which is usually a sum, finite sum of tensor product of operator on S and M. And the last point is that in general in this scheme, the measurement operator has a spectrum which is highly degenerate. Since when you measure only M, the measurement operator is the identity on the system, and it is, in fact, usually an operator which has a non-degenerate spectrum on the matter. Okay? It is just this. If you combine these three things, you can write down first the simplest model of a photon box with these things. So how to do that? First, the tensor product. The tensor product, so the photon, it is the simplest infinite dimensional quantum system that you can imagine. Okay, imagine it is, in fact, a quantum harmonic oscillator. So you have a Hilbert basis with this Hilbert, with this vector, with n is equal to 0. 0 is the vacuum. 0 photon, and n is equal is 1 photon, and so on. Okay, so you have this simple fix. The matter, it is the simplest finite-dimensional quantum system that you can imagine. It is a two-level system with atom in ground state or in excited state. Okay? And the state of a composite system, it is something like this, where you have, in fact, two quantum numbers, n and eg. Okay? So you can write down the wave function of a big system, okay, as, in fact, a wave function g on the small system tensor something, and another vector tensor something on the photon. And you see the orthonormal basis is this one. It is completely different with respect to the Cartesian product. For the Cartesian product, all what I have to do is to complete. I take the basic here, the basis here. I had E and G, and it's enough. Here I have to mix them. Okay. So, and now what's going on? So I just consider, in fact, the evolution here. So let us consider the evolution when one atom gets outside the box here. It has nothing to do with the photon, which means that the wave function at just outside the box of the big system is a separable state. It is the wave function of a photon, psi here, infinite dimensional, and we assume that we prepare the atom always in ground state. Then when I consider all this evolution, I will not enter into the detail, okay? It's a unitary evolution. It is governed by Schrodinger Equation, which means that here, just before the detection, you have the big wave function is a unitary operator times this guy. And which means that you can always represent this as a linear operator mg on psi tensor g and me of psi tensor e. Because u, with respect to psi, it is a linear mapping. When you fix g, you consider with respect to psi, it is a linear mapping. Okay, and because whatever the evolution here is, because u is unitary, what you have this partition, in fact, of a unity operator. It is true for any evolution here. Okay. And now let's have a look at what's going on during the detection. So just after the detection, you have this wave function, which is not separable. You cannot factorize the wave function as a wave function, a vector on the photon, tensor, a vector on the atoms. But when you measure this operator, okay, what you have, in fact, two detection outcomes. Either you are in E or in G, okay, ground or excited. If your detector say G, okay, then you have to use the collapse. You only take this part of the wave function, and then you normalized. So just after the detection, in fact, the wave function is separate. You know what is the state of the atoms? It is G. And what is the state of a photon? It is this guy. And this is exactly what is called the measurement back action. Okay? And what you know is this probability here, it is the probability to detect Y, knowing the wave function just after the detection. Just before the detection. Okay? This is this. So which means that with this rule, you can define what is called quantum trajectories. Quantum trajectory is just this. You initialize psi to a certain psi 0. And then at each time step, you can, in fact, define, which branch you have to choose by using this probability law. And the probability law, the repartition, depends on psi. Okay. So here, it is important to understand what are the computation here. So you see, I have three evolution. You have an evolution when you are here. It is you R1. You have an evolution which is the composite evolution, atom plus photon. Okay? Here you manipulate only the atoms here. Here you have an evolution, a joint evolution atom-photon, and here you post-manipulate. Okay? You can, it is, so despite the fact that the wave function is entangled, you can still locally manipulate the wave function, okay, of the atoms. So which means that when you look at what is UR1, it is identity, of course, on the photon. But here you see it is an operator which is just, in fact, a rotation of pi over 4. Okay, because it sends G to this diagonal vector, and it sends E to another diagonal vector, which is orthogonal to the first one. So it is just a rotation. What is this evolution here? It is, in fact, a conditional phase. When the atom is in G, you put this phase on the photon. So it is this operator is a diagonal operator where n is the photon number operator. And when the atom is in E, you see, you put another phase on the photon, which are different. Okay? And then you assume that the second evolution, so the evolution after the interaction is the same as the evolution for the atom, is the same as the evolution for R1. This forms a Ramsey zone. So let's do the computation like this. So look, how to do this here. Just replace G by this guy. So when I replace G by this guy, I obtain this factor, and then I have psi tensor G plus psi tensor E. When I want to apply this thing on this guy, so what I know is that when I am in G, I have to put this operator on the photon, and when I am in E, I have to put this operator, which means that it is just replace when I am in G, phi by this guy, and when I am in E, phi by this guy. Okay? And now continue when you can use the post-manipulation of the atoms. Just what I have to do is I use these things again, which means that I replace G by G plus E, and I replace E by minus G plus E, which is exactly what I have done here. Okay? You have this factor 1/2. Okay? It is G becomes this guy, E becomes this guy, and then at the end I factorize. I put G on one side and E on the other side. Okay? And what you obtain is something which is the sine and the cosine. And this gives you the two measurement operator. And you see that mg dag mg plus me dag me, it is 1 because cosine square plus sine square is equal to 1. Okay? And with this, you can do small simulation. It's very easy to do some simulation with this. It is quantum Monte Carlo simulation. So, and I have written for you a small MATLAB script for that. So, here is the script. You see, the entire script is here. You have graphics here. You have a declaration of variables here. Some basic, which is M is the diagonal operator with a photon number, sine, the cosine of a photon number. So it is just diagonal operator. Here I have put an initial state corresponding to a coherent state with 3 photons, a state which is easily to prepare, what you can prepare easily in the cavity. And then the only things that you have to see, it is something important to know. What is a Monte Carlo simulation? It's just this. So I have psi, which is in fact the state of my system. It is initialized here. I compute the two projections on G and on E, okay, with in fact the probability. I take a random number generator uniform between 0 and 1. If rand is less than PG, I choose, in fact, the G branch, and else I choose the other branch. And then I iterate. Just this. And if you do that, you obtain something like this. Okay? This is one realization of this stochastic process corresponding to one experiment. Okay? In the ideal case. So if I take another realization, starting from exactly the same thing, I obtain another thing, and so on. And what is in this, with this operator here, what is magic is that, in fact, at the end, you converge always to a photon number state. Okay? But it is not deterministic. Okay? So you see that with this small MATLAB program, you can represent in a quite, I will say, suggestive fashion what's going on in an experiment. Because in the experiment, what you know is this. Okay? It is your sensor. So all what you have to do to follow, in fact, the state of your system is just to take this round number, but just to apply, you know, from the detector which branch you need to use. And it is called a quantum filter. It is just this. Okay? Well, so now this was my introduction to quantum physics from scratch. So, okay, so maybe it's a little bit too rough, but now I will go to the BB84 quantum K distribution. So the idea, so I borrow this slide to a course of Serge Haroche, one of his first courses, I think, at Collège de France, where it is very, very nicely, in fact, explained. So it is Alice and Bob, always, and they want, in fact, to share a key that will be, in fact, a key that you can use after that with a classical cryptographic protocol. So it is an encryption key here. So the way to do that is that Alice, in fact, sent to Bob on a quantum channel. This is the quantum channel here. Okay? She sent to Bob photons, which means, in fact, qubits. Either they are horizontally, vertically polarized, or they are, in fact, with a rotation of 45 degrees, okay, like this. And she sent the photon in a random way. So she decides in a random way, either she takes this guy, this guy, this guy, or this guy. And then Bob, at the other side of the transmission line, okay, what he chooses in a random way, he chooses, in fact, the measurement he will perform on the photon. It is in the random way. So Alice sent in a random way, okay, uniform distribution of around this four state of a photon. And Bob, all what he do in a random way for each photon, he choose in which basis he will measure it. Okay. So when you look, for example, for this photon here, so this is a photon sent by Alice. You see that this photon, it corresponds to 0, the bit 0. And when you look, Bob, independently, has chosen, in fact, the good basis. So he will obtain 0. Here, if you take this photon here, it is vertically, in fact. And Bob chooses the good basis, compatible with this. So no problem, it will be obtained 1. Here, it is something where, in fact, you do not detect anything because it is an error rate. This one, it is in the good things. And this one is not in the good things, you see. This one, it is horizontal, but Bob chose the bad basis, and so on. So what you obtain, Bob obtained these results. OK? So this is exactly what they got. They got these results. And after the protocol, the way is they use a classical communication protocol, where, in fact, for each photon, Alice do not send what is the value of a photon, but what is the kind of polarization of a photon. And Bob sent to Alice what is the kind of polarizer used to measure the photon. And they keep only, in fact, the photon where, in fact, the polarization coincides, but not the value of the photon, only the polarization. OK? So it is this thing. So here it is recalled, in fact, with some quantum, with a qubit state and so on. Okay. So this is the n linearly polarized photon along 4 possible directions. And the directions are not orthogonal, which is the key issue. And here it is the measurement, in fact, performed by Bob. It is either he measures Z, okay, or he measures X. Okay. And then the second part, which is the communication, the public channel communication, they exchange, in fact, the color. They just exchange the color, blue or magenta. So you start with a large number of photons n. After this first step, you obtain n over 2 in average. And among this n over 2, in fact, they take half of this number, or the large part of this number, and then they exchange the values. If the values coincide, they are convinced that the communications channel, the quantum communication channel, has not been spied. And then they will use the other photons, which is n over 4, which gives them, in fact, the key. Okay, it is the protocol. And what is, in fact, the key issue to ensure the security of the protocol is that if Oscar spies the line, he will perturb it. So he will perturb the photon, and he cannot clone the qubit sent by Alice to Bob. He cannot take the photon, clone it, okay, in a certain number of times, then measure it, then he will know what it is, and then send one of the clone to Bob. It is not possible to do that. So with this protocol, of course, if you are spied, you cannot send you cannot exchange the key, but you know, in fact, that the quantum line has been spied. And it is important to, because the no cloning theorem, it is a very simple theorem, okay? And the proof is here. It is due to Zurek. It is a very simple proof, so I'm very jealous, in fact, because it is very interesting. It is a very good paper because it is a paper that a lot of people understood, in fact, and with important impact. So it's the best paper that you can do is this kind of paper, in fact. So assume that you have a machine that can copy. So initially, what you have your qubit state, the clone qubit here with the initial state, which is B, and you have here, in fact, the state of the machine. And since you want to have a copying process which is independent of psi, okay? When you copy, for example, a piece of paper, you push a button and you always launch the same process, which means that with the same unitary evolution, you should have this thing. I start with psi, with B and FB, and with the same unitary evolution, typically I should have psi, tensor, and here, of course, the state of the machine could depend on psi at the end, because typically in classical machine, the ink level can change depending on the quantity of character that you have on the page that you have copied. But once you have this, you can prove, because you have to copy, in fact, two states that are not orthogonal. That is the key issue. Okay? The fact that the states sent by Alice are not orthogonal, it is the key issue. Because in this case, what you have is when you consider the dot product, the Hermitian product between this guy and this guy, so it should be the Hermitian product between this guy and this guy. So the Hermitian product between this guy and this guy, it is not very difficult, but it is 1 over the square root of 2. Since U is unitary, it should be the Hermitian product of this guy. And the Hermitian product of this guy, because it is a tensor state, it is the Hermitian product between this and this, this and this, and this and this. And what you obtain is something which is a contradiction. Okay, so you cannot copy, just because of that. So now I guess that you know how to manipulate, in fact, Hermitian product between tensor tensor space. Okay, these things. It's the way you use tensor product here. The short factorization algorithm. So here it is a little bit more tricky to explain this, but maybe. Here is the algorithm that you can find typically well explained, well described in the Nielsen-Schwank book, classical book that has been published in 2000. So what is the algorithm? The algorithm is just this. You have as input a composite odd number, of course, not even. As output, it produces you a non-trivial factor A of n. But it produces this in how many operations? So it is, you take n, you take log of n, which is the size you need to store n, the number of bits typically, and you have something which is, in a certain sense, quadratic. Quadratic with respect to what? To respect, in fact, to the universal classical quantum, classical and quantum operation. So classical operation, you know what it is. It is the two elementary gates, AND, XOR, for example, and NOT gate. With this, you can do everything, okay? But here, for quantum operation, what is it? It is typically quantum gates. And quantum gates, which is a quantum gate, is just a unitary evolution. And you have quantum gates for just 1 qubit. So it is a rotation in the complex plane. Okay? So you assume that you have at your disposal any rotation in the complex plane. Okay? You can do that. And for another, to be universal, you need also gates between 2 qubits. And you need only to add one gate, which is the CNOT gate. Okay? It is just this one. So you are in the 2-qubit space. Okay? So the basis, to define a unitary evolution, you need only to define it. You take an orthogonal basis at the beginning, and you have to decide what is the orthogonal basis at the end. Okay? So I take as orthogonal basis this one. And I will just make a permutation of this thing. And here it is the control bit. So when this one is to 0, you don't change this one. Okay? But when this one is to 1, you flip. Okay. So if you prefer, it is this matrix. If you prefer, but it is exactly this. Okay. So if you have this gate and any rotation in the complex plane, so for each qubit that you manipulate, okay, then you can generate any rotation for the n qubit state. Okay. So this is in this sense that it is, in fact, a fast algorithm, which means that it is a polynomial. It requires a polynomial number of operation of elementary quantum gates. So the algorithm, in fact, is a mixture of classical computation and quantum computation. So I will not enter into the details, but at the end, it reduced, in fact, to the problem of order finding, which is a problem of an arithmetic problem. Okay, you take x, okay, a number less than n. You assume that x has no common factor with n, and you want to compute the smallest exponent r such that xr is equal to 1 modulo n. It is the order of x. And it is known as a difficult problem. Okay. And what is interesting is the random part in this algorithm. So what you do is you start this, you compute the order n, and then you have two branches. Either the order is even, and then you can, in fact, compute, in fact, and if these guys are between this and this, then you have one one divisor, okay, of n, or you can fail. But you fail, what is important, with a probability which is strictly than 1, okay? And the bound with respect to 1, you have a margin, okay, independent of n. N is a large number, so you consider the asymptotic. When n tends to infinity, the probability here doesn't tend to 1. So you have a certain probability to succeed. Okay? So if you repeat this a certain number of times, you will find some A. And for this, what you have to do is to choose randomly a number between 2 and n minus 1. Okay? So this is the complete algorithm. So I will not enter into the details of how to compute the order of a number modulo n. I will just, in fact, maybe skip this guy, but go to this guy. At the central point of the algorithm is the quantum Fourier transform. So the quantum Fourier transform, it is for signal processing. What is well developed is, in fact, the discrete Fourier transform. The discrete Fourier transform, of course, you use this, okay, on a vector whose length is a power of 2. So 2 power L. So you have two complex vectors. And you know that between these two complex vectors is just, in fact, a unitary evolution. Okay? Defined, in fact, by this formula, when you recognize typically the formula, classical formula of a discrete Fourier transform. And you know with a fast Fourier transform, you have an algorithm where you have L times 2 power L, addition and multiplication. Okay? This is the complexity. Okay? You give x as input, and how many computations I have to do to obtain y as output, I have to do this thing. But this thing, it is quite amazing. It is, in fact, a unitary evolution, which means that you can represent this as a big rotation, okay, in the Hilbert space, which is C2 power L. But C2 power L, it is, in fact, an L qubit. So when you consider, in fact, the index of the N qubit here, so the basis, G, okay, 0, 1, 0, 1, 0, 1, okay, then what you obtain here is, in fact, another formulation of exactly the same formula here, exactly the same thing. But what is amazing here, so you take G to this superposition of G, in fact, okay? What is amazing is that for any G, this guy is a tensor product. It is not obvious at all. There is a formula telling you that when you take the Fourier transform and see it as a unitary evolution on an L qubit, okay, it sends, in fact, you take the natural, in fact, tensor basis. It sends the tensor separable basis to another separable basis. And it is with this formula here that I will not explain that you can, in fact, ensure a very efficient, in fact, quantum circuit, okay, to compute this guy. It is this thing. So what you use to do that, I will not enter into detail, but just I give you the main argument, is here how to read this, in fact, this scheme. So you start from the initial basis. So the way to, there is a little bit things to understand in the notation. Okay. So I want to define to G, I have to associate something. But G for an N qubit, L qubit, it is G1, tensor G2, tensor GL, where here I have used G is equal to sum of GL, GK, 2 power L minus K, for K is equal 1 to L. Okay? It is when I write the number in the basics 2. Okay? And here I have either 0 or 1. It is either 0 or 1. So you have to be aware of this way of labeling, in fact, the basis. So, and the fact here, so you have a G at input, which is this guy. And you see that I use always the same, in fact, quantum gates. So what are these quantum gates? H, when I have only a quantum gate, a block on one wire here, it is only, in fact, a single qubit quantum gate. And when I have this guy, it is just a control, in fact, R quantum gate. So I will explain what is this. Okay. So look, here it is time 0. Then I start with Hadamard transformation of G1, which is the Hadamard transformation tells me that when I am in 0, I put this, and if G1 is equal to 1, I put this. Okay? Third step here. Then I put here, just to understand what's going on control R2, which means that when G2 is equal to 0, I do nothing. And when G2 is equal to 1, I put exactly this transformation on the first qubit, where K is equal to 2. Okay? It is just this. I continue. So I continue, talk, and I do all the qubits like this, and I finished here by the last cubic, okay? And which is, if it is in 0, I do nothing, and if it is in 1, I apply this rotation, okay? This phase, in fact. It is a phase. I put a phase on 1. I obtain this phase, in fact, with K is equal to L. And then I continue with the second one and so on. And at the end, I obtain almost this guy, up to, in fact, a reordering. Okay. It is just this. So you see, this is the way just to illustrate. I guess that this thing is just to illustrate what is, in fact, a complex quantum gate, which corresponds to the quantum Fourier transform, that you can, in fact, decompose in an efficient way. Okay, you see that you use only L2. If you count, you have only L2 gates here. In an efficient way to compute, in fact, this big unitary evolution. You see, you have to define the unitary evolution in an Hilbert space of dimension 2 power L. If L is 1,000, it's not so simple. But you need, if L is not only 1,000, you need here only on prend 1000, c'est 2000, 1 million of gates. Only this, elementary gates, to compute this. Elementary quantum gates. And what is behind this? Behind this is the fact that each, in fact, elementary quantum gates take, in fact, a small number of time, which is always the same in a certain sense. Okay? So it is the way you recognize sort of parallel between classical and quantum complexity when you define what are, in fact, my basic resource. And I want, in fact, to use this basic resource in a very economic way. So I think it's time to start the second part. So it will be on quantum error correction. So first, I will start with classical error correction. So classical error correction. So here it is written here, but what you have is this. You have a single bit, B, okay, which has a certain probability to flip per unit of time. So around the sampling time, it has a certain probability to flip. So typically for usual bits in dynamical RAM, okay, what you have is the probability, in fact, to slip during the time delta t is this guy. So it's something which is quite small. Okay? Okay, so almost for in our computer, the probability to have a bit flip in the memory of your computer, it's quite very, very low. Okay. But in any case, when you go, typically you need some error correction, typically when you use some computer in space, because you have a solar radiation that in fact increase this bit flip. Okay. So how to do that? It is something what you use redundancy. It is something very completely stupid. You use, in fact, 3 classical bits to code a single logical qubit. Okay? And when, during the time delta t, say that only 1 qubit flip, okay, you obtain this. You know that if you assume that there is only 1 qubit because you use a majority vote algorithm, okay? So if this one is different to this one, which are equal, then you corrected, correction, measurement and correction, and you recover B, B, and B. Okay? It is exactly what I have written here. It is 3-bit code, something elementary, completely elementary. And so what you assume is you let the evolution during delta t, and you assume in this simple model that the measurement of a qubit, so you measure this, is instantaneous, okay, first, and that the correction also is instantaneous in this thing, okay? And in this case, what you have is to do some probability count, how many times, because I can have 2-bit flip, okay? I can have 3-bit flip during the time delta t, okay? So you count what you have. You assume, of course, that the each bit flip, okay, flip with a probability which is probability law, which is independent with respect to the other bits, okay? You use this, so this is your model of error, okay? It is something which is local and independent, okay, always. And then you compute what is now the probability that you flip here after the correction, because you can correct 1 bit, but with this code you cannot correct 2 bits. Okay? In this case, you will have a bit flip after the correction. And you see that you start with p and you obtain p squared. Okay? Which means that p is very small, typically is equal to this. If you use this kind of, in fact, correction scheme, then you obtain something which is very, very small. So it is okay. Okay. Just one level of correction is okay, okay, to have something which is, in fact, forever in a certain sense. Okay. Voilà. Bon. So it is something quite almost a simple exercise. What's going on for quantum system? So for quantum system, so time will be discrete, of course. Everything is there for what is called the 3-qubit bit flip code. So I will spend some time on this slide because it is important. So you first start with a model of error. It is very important, this model of error. It is local. So you have, in fact, each qubit, each physical qubit can flip completely independently of the other one. And you have a flip probability during the time delta t, which is p, exactly as here. But what is a bit flip for a qubit? Bit flip. So it is when, so my qubit is this one. So I have a store inside my qubit some quantum information corresponding to the amplitude, complex amplitude alpha and beta. And when we bit flip, so 1, 0 becomes 1, and 1 becomes 0. It becomes this. You assume that you have only this error. This is the simplest error that you can imagine, just to you reverse. Which means that it corresponds to beta 0 plus alpha 1. So you exchange alpha and beta. Okay? And the difficulty is that you cannot measure to recover this. The measurement process, if you measure, either you obtain 0 and 1, and will use what is alpha and beta. So you cannot just measure this. You have to measure something, of course, which is the measurement syndrome, to see if there is a bit flip or not, but you cannot have a direct measure on this. what you do is you will encode your qubit, your logical qubit, Psi-L. This is Psi. Psi-L, it is alpha, and I take 4 copies here. And what I assume is that this qubit, this one, okay, can flip with probability P during the time delta T. Independently, this one can flip with probability P, and independently, this one can flip with probability P. If it flips twice, it's not a problem. It's you recover the same value. So you don't care. Okay? And what you are doing is this. Assume that you have only one flip, okay, on one qubit. What are the possibilities that you have? So either it is the first one that flip, so which means that this guy becomes 1, and this guy becomes 0. Okay. I assume that the second flip, so it is the qubit which is in the middle, and the last flip, it is the qubit which is at the end. If I have 2 flip, okay, here I assume that the 2 first qubit flip. Here I assume that the 2 extreme qubit flip, and I assume that the 2 last qubit flip. And if I have 3 flip, okay, in this case, the 0, 0, 0 is replaced by 1, 1, 1, and 1, 1, 1 is replaced by 0, 0. It is the only possibility that I have. But what is very important is this thing, is the fact that when you look, in fact, at the plane, because this thing defines the plane, okay, with respect to alpha, beta. Assume that alpha, beta are any arbitrary number. So this thing generates a plane when you change alpha, beta. This one also generates another plane. And this plane here is orthogonal to the initial plane. Okay? So what you see here, that when I have any number of flip on completely independent of a qubit who flip, in fact, I have jump between what? Between, in fact, 4 orthogonal planes. The first orthogonal plane is spanned, which is called the code space. It is where you want to store your quantum information. You have a first, in fact, plane orthogonal to this one. It is when you have just 1 bit flip. You have a second, which is where it is, in fact, the second which flip, and the last one, which is the last flip. And this plane is orthogonal to this one. This plane is orthogonal to this one. And this plane is orthogonal to this one. And this one is orthogonal to this one. And this one is orthogonal to this one. So you have a collection of 4 orthogonal planes. So if I do a geometric picture, what's going on? Here I start in the code space. And what I can do, I can either jump here, or here, or here. OK? Just this. So it is clear that, and I am in, so here it is dimension 2, 2, 2, 2. So at least I am in an Hilbert space of dimension 2 plus 2 plus 2 plus 2. It is 8. It is 2 power 3. So I explain. So what I have is, in a certain sense, something like this. So I have a block here, a block here, a block here, and a block here. And now it is not very difficult to see what is a measurement on this big space. It is an Hermitian operator. I can assume, so if I put here the first one, P1, P2, and P3, Okay, this is my big map. Okay, I have to define what? A measurement operator that gives me either I am here, or I am here, or I am here, and I am here. And since they are orthogonal, it's possible. Okay, it is just this. So the trick of quantum error correction is, in fact, to encode, of course, the qubit in a larger space, a multi-qubit space, okay, the logical qubit. And for each error, you have to jump to an orthogonal space. Okay? In this case, what you can do is you just can measure, okay, with a measurement operator which has these things are degenerate in the degenerate part of the spectrum of the operator. Okay? The eigenvalue of a measurement operator should have a certain multiplicity. Okay? And all these guys have to be included into the eigenspace of a measurement operator. And in this case, it is okay. You will not touch, when you measure it, to alpha and beta. You will only see in which block I am. So the trick here is just this. So the measurement is what is called the error syndrome. So you consider this operator. So what is this operator? S1, syndrome 1, S2, syndrome 2, and S3, syndrome 3. Here. So let's have a look at S1. S1, it is identities to the first one. It is Z to the first two, and Z for last one. Okay? So what are the eigenvectors of this thing? See, it is here. If I take S1 on G1, G2, G3. Okay, what is it? It doesn't depend on this because it is identity. Z on G1, okay, if G2 is equal to 0, okay, it corresponds to +1, phase +1. Okay, Z, remember Z, it is written here. Okay, 0 is the eigenvalue +1, and 1 is the eigenvalue -1. So this thing, it is -1 power G2 plus G3, the same thing. Okay, so it is what is called a parity measurement. So when you see, and you do that for, put the one here and put the one here, and the other things are okay. And in this case, what you can check is that these are free commuting observables, so you can measure them without any problem. And the measurement outcome, it will be this thing, so it will be S1. Either it is +1 or -1, I don't care. So if all the measurement S1, S2, and S3 are equal, then either, look here, either I am here, no flip, or I am here. Okay? Either I have 0 flip or 3 flip. Otherwise, all these guys are not in the same parity. Okay? So what I do is I do no correction. When typically the first one is different to the two other one. Okay? What I obtain here? Okay? I obtain either it is the first one to flip, or either what I have this 2-bit flip with this guy here. So I permute alpha and beta. And what I do as correction, just I apply the unitary evolution, which corresponds, in fact, to an exchange of 0 and 1 on the qubit 1, and do nothing on the other guy. And I recover, jump back to the code space. And you do exactly the same thing for the two other possibilities here. Okay? It is just this. So the main trick is this. Okay, you see you have your local error model. You encode your, in fact, logical qubit in a multi-qubit system such that your local error model shows that your logical qubit jump, in fact, to different orthogonal planes. And then you have to engineer to see what are the measurement syndrome to see in which space I have jump. Okay? But you don't touch to what is inside here. And with this kind of things, what you, in fact, correct is only 1 bit flip, of course. You cannot correct 2 bit flip. Okay? That's the main trick of error correction. So you can still measure, but you have to measure something which is, in fact, more subtle. And last point, it is important. So I have a local error. Okay? The measures are local. The corrections are local, because I put correction only on each physical qubit. But something which is not so simple is the measurement, syndrome measurement is not local. To perform this kind of measurement is not easy. The parity measurement between 2 qubits is something which is not so easy in practice. To do this, it is something that it is easy to do. Okay? But to engineer and to, in fact, have on a real platform measurement of a syndrome is not so easy. Okay? Well, is it clear, this? And now, you can imagine other kind of error for the qubit, not only a bit flip error associated to the error operator X, okay? When you exchange alpha and beta. So you have also what is called the phase flip. The phase flip is just, instead of when you have a phase flip on this qubit, you put a -1 in front of beta. Okay? But what is nice with phase flip is that it is almost the same as bit flip, because you have a conjugation with the Hadamard gate. So the Hadamard gate, it is this, in fact, unitary transformation, which sends 0 to 1 plus 0, and which has 1 to 0 minus 1. Okay? It is not a rotation because the determinant is -1, but it is a unitary operation. Okay? And with h, you can realize that h square is 1. So it is the square root of the identity matrix. Okay? And the second point is that x, it is, in fact, z, but in the frame h. Okay? If you change a frame, which is a unitary evolution, and you consider what is x, it becomes z. And because h square is equal to 1, if you consider z, okay, x in the h frame, it is z. So you have a complete correspondence. And for the state, it is this one. So what is the eigenstate plus 1 of z? Okay, it is 0. And it corresponds to the eigenstate plus of x. Okay? When you permute this, you obtain a +1. When you permute 0 and 1, you obtain -1. It is as 1 here. You see, it is exactly this. So all what you have to do to obtain the bit flip, the phase flip code, if we have only this thing, it's just, in fact, to replace 0 by plus, 1 by minus, x by z, and z by x. And that's it. Okay, and this is exactly, but in a smaller character, okay, this thing. Okay. When I have put 0 by plus and 1 by minus. Okay, it is just this. So I won't get into it. And once again, you have 4 orthogonal plane and so on. It's the same thing. Okay. But here you cannot do more. If you have, for example, at the same time, x and z, either bit flip or phase flip error on the same qubit, here, you see, you need at least here dimension 8, but you are already in a space of dimension 8, so you cannot use this space, in fact, to make error correction with phase flip and bit flip, because you need space. You need more redundancy in this thing. So, and it is the big idea of Shor, once again the same guy, around the same period, quite a clever researcher, Peter Shor, in fact. In fact, very clever one. what you do if you start with plus, 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 and minus, 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 so the code for the phase shift, and you replace x plus, h plus, and x minus by, in fact, you encode the 0 in the plus and the 1 in the plus by 0, 0, 0, and 1, 1, 1. So you sort of merging the two things. So which means that plus becomes this, minus becomes this, and then you have plus, 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 minus, 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 which means that your logical qubit is now not in with 3 qubits, okay, physical qubits, but your logical qubits is in fact supported by 9. Your logical qubit is supported by 9 physical qubits. You are in this space, and the logical 0, it is, you see, you obtain it with this logical 0, but when you in fact expand plus by this, the plus by this, the plus by this, but so what you obtain is exactly this tensor product here, where here I have 3 qubit, 3 qubit, 3 qubit. It is all this thing is tensor product, okay? So I am in a 9 qubit space, okay? And the other one, the 1 is the same, but I put just a minus here, okay? And in this code space, what are the local error? The local error, they are on the 9 physical qubits. They can either add bit flip x, phase flip z, or a bit flip followed by a phase flip. So if you take a bit flip followed by a phase flip, what you obtain is the transformation xz, which is, when you use the usual Pauli matrices, it is E times Y, which is the last Pauli matrices, but we haven't used yet. It is this guy. It is another square root of an identity operator. And what you can prove, so it is not so simple, but you can check that with this process, I have how many, in fact, with this? So my code space, it is spanned by 0L and 1L. When I have error qubit 1, I have 3 possibilities for error of qubit 1. So I have this, or this. Okay? Error qubit 2. I have 3 possibilities, this, or this, corresponding to x1, z1, or y1, x2, z2, or y2. And the last one, it is x3, z3, and y3. Okay? Ah non, comment j'ai obtenu ça? Okay, and I continue until the 9 one. Okay, I don't know which qubit has jumped. So I have 9 qubits. Each qubit can jump. So what I have at the end, how many planes I have? I have, in fact, 1, this one, plus 9 times 3 to have all this plane here. And you can check that they are all orthogonal. But it's not so easy. How to check that? So it's, and it is, I think the best way to check that is to use what is called the stabilizer code, which is, it is a way, in fact, to do computation in this quite huge dimensional space, because it's 2 power 9. Okay, how to do computation in C 2 power 9. Okay, it's not so easy. So there are tricks to do that, and it is typically the trick of stabilizer code. It's the way of doing compact notation with the Pauli matrices of, in fact, of these things. It is the main issue of stabilizer code. Yes?
Is it the minimal way?
No, no, it's not the minimal way with respect, in fact, to the dimension of Hilbert space. So, and here, what is the minimal dimension of Hilbert space you have here? You need, in this case. So you have 2 power n. It has to be greater than 2, the number of this orthogonal space. So it is 1 plus 3n. Okay? Which means that it is OK with n is equal to 5. And with n is equal to 5, you have such kind of code. But it is clear the way you store the logical qubit 0L and 1L is not the same thing here. You only use a 5-qubit thing.
Instead of using projective measurement and using UVM, you gain something?
No. It is here. It is explained here. Assume now, and now you have to understand. So you have this thing, and now you will assume that I have other errors, but there are errors that are linear combination of. So an error, it can be seen as a measurement operator M, which is a complex coefficient times identity, plus another complex coefficient times x, plus another complex coefficient times y, plus another complex coefficient times z. Okay? With this, I represent any operator, Hermitian or not, on a qubit. And if I measure this operator, I use my rule. Okay? I use M, I plug M on this. So which means that I have this, in fact, error operator on a qubit, general one. I say that it appears on qubit K. So I put it is MK, which means I tensor times identity to the other one. And what I obtain, in fact, is the transformation of my logical qubit into this things with what it is. It is a linear superposition when I am here, for example, here. It is a linear superposition between the code space, if it is the first qubit, this one, and this one. Okay? And now assume that I have a syndrome measurement. Okay? Syndrome measurement, when I will measure, I will in fact focus on one on this space. Because it is a Q&A measurement. So I will not touch to what it is in space. But if there is something, I have a probability to either converge here if it is not 0, or converge here if it is not 0, or converge here if it is not 0, or here. And now I know if I am here, or here, what to do to correct. So which means that it is a kind of miracle when you correct only 3 basic errors. Okay? You correct any qubit error that could vary with respect to the time. Because of this. It is something which is very, very important, in fact. It is something which is completely different to what's going on in the classical case, where the error on a bit is just a flip. And it is discrete. Here, M could be a function of the time, which is continuous, and so on. Okay. And this is the main trick here. I think the only things that you have to, in fact, to retain is this geometric picture. Okay? An error, in fact, you have a transfer to an orthogonal plane. Okay? And you use the fact that it is exactly the extension of what I have shown on the phantom box, nothing more. It is the basic quantum rules. What is noise? It is an unread measurement. Okay? What is decoherence? It's just the environment that measures fictitiously your system. And with this trick, you see that you correct any qubit error. Okay. Yes?
Correct those 3 errors, but you can also have an arbitrary phase.
Yes, yes. And in this case, if I have an arbitrary phase here, not a problem. I put C, which will be the arbitrary phase. I can replace always this kind of error, for example, this operator. I can decompose it as a linear combination of identity x, y, and z. Because it is a basis of a 2-by-2 operator, just this. And what I recover, if I want to be very precise, in fact, with this, I recover, in fact, the logical qubit up to a global phase. Okay, but it's not important in this case. Okay. C'est bon. So this is, in fact, this is the main issue on error-correcting codes, in fact. Starting to understand this, I think it is important, this. Okay? And then it is clear that when you have measure here, you know where you are. Either here you do nothing. If you are here, you put x1, z1, or y1 if you are in the free things. Okay? It is exactly this. Okay? And with this, only local control. I just look at my qubit, which is here, my physical qubit, which is here. Okay. So what are the open issues connected to quantum error correction? So it is something which is very interesting indeed. So I have already a response to a question, and you have a code for n is equal to 5. You have also a code, a famous code, the Steen's code, I think, for n is equal to 7, I think, which is, from a practical point of view, more interesting to experimentalists. You have over a lot of things. So so you have how to do efficient construction of quantum error correcting code. Since you are in quite large Hilbert space, you need a sort of notation. And notation is with what is called stabilizer code. Okay? It's a way to do the computation in these things, and in particular to define what are the good error syndrome. Because I see here, okay, but what are the error syndrome? And one of the key issues is since you have local error, you want to have error syndrome which are, of course, not local. You cannot have them local. But the most local as possible, which means that you will, in fact, measure the parity typically between neighbor qubits. And it is called surface code, this thing. Okay? And how to do this when you put your qubit on a grid, okay, on a lattice, and you want, in fact, only you have access only to each qubit independently to correct, and you will have to have only local measurement of a qubit and its neighbor. And this is called surface code, this. And you have a lot of very Kitaev and so on. There are a lot of very clever development on this, okay, for this thing. You have also things that when you are inside the code space, okay, you stay here at least forever. But you want also to manipulate. You see, for doing a quantum Fourier transform, I have to manipulate my qubit. And my qubit will be a logical qubit. So how to do the computation, the manipulation, the gate, but in fact, encoded quantum state. And what should be tolerant to errors. Because error, when you do this, you have an error on one, you do a gate, it can propagate to the other one. So you have to have some kind of clever way to do computation, avoiding propagation of errors. The same thing, in fact, for the measurement. When you measure, when I measure something here, I have not to touch there. Okay? I have to do something clever. Okay? So the measurement should be also tolerance, fault tolerance. Okay? So all these things are important. Okay? Okay, so do not propagate local errors. And then when you see the difference of lifetime, I will say, of bit, and I will say good superconducting qubits, 1 millisecond, okay? You see that there is a large, in fact, order of magnitude, which means that if you want to correct a qubit to reach this error rates, okay, you will need so very high order correcting codes. Not only you do not have to correct one qubit, but you will have to correct 2-bit flips, okay? If you correct 1-bit flip, you replace p by p squared. If you can correct 2-bit flip, you will replace p by a constant time p power 3, and so on. So if p is small enough, okay, the quality of your qubit will increase. And the P is small enough is a threshold theorem in this case. So all these things. And, okay. And if you look at some for surface code, typically, the first estimation was by Martinis group. It was, I will say, 1,000 physical qubits to store one logical qubit. So you see that the estimated overhead is quite large, which means that to store logical qubit, which is in a complex plane, you need to be in the Hilbert space of dimension 2 power 1,000. So it's a little bit strange, I will say. So maybe it could work, but it is okay. So in 10 minutes, yes, I will finish in 10 minutes. So it is something where more or less we are working with the group of Maziar Miraimi, Zaki, and Alain Sarlet, who are in the room, okay, in the quantum T, which is between Paris, ENS Paris, Inria, Lemin, and also Yale, okay? And it is about continuous time, quantum error correction, and feedback. So you see, what is quantum error correction? You have your system, you measure, and depending on your measurement, you do an action. It is a feedback scheme, okay? But it is a very simple feedback scheme. It has no memory, which means that it is what is called in control engineering, it is a static output feedback scheme. You have your system, you measure something, and the control is a static function of what you measure. And the simplest regulator, it is called in quantum engineering, it is the proportional regulator, the P regulator. Okay? It is the simplest way you can imagine to do a feedback. Clearly, what you can do is you can take a feedback. It is called Markovian feedback in the physics literature due to, it is Weissman here. But usually, in the discrete setting of quantum error correction, the measurement, which is called in engineering the sensor, and the correction, which is called the actuator, okay, they are assumed to, in fact, achieve instantaneous process. But in general, they have a finite bandwidth. Measurement is not instantaneous, and correction is not instantaneous. So there is a natural question how to take the finite bandwidth of your measurement process and actuation process, okay, into quantum error correction. And in this case, it's not so easy to do that. And there is a clear interest to, in fact, develop continuous time formulation of quantum error correction. Okay, where, in fact, the measurement and correction will have to be much faster than the error rate, of course. Otherwise, you cannot correct everything. But not infinitely faster. So you will have some small correction. Okay, and when you see the precision we need, okay, for, in fact, the fidelity of a qubit, you need to take into account these small effects. Because now, people manipulate qubit with precision less than 1%, okay? So to increase precision, it will be a difficult task. And you will have to take into account these kind of things. And also, there is another point, is that the qubit error could appear during the measurement process or during the, in fact, the correction process. And you don't know when it appears. It could appear at a certain time if, for example, it is a desexcitation. So if the measurement, the M, it is the sigma minus, so it is the 1, but is sent, no, it is in 0 is the excited state, and 1 is the ground state in quantum information. So you go from excited state to ground state. So this is a sigma minus. If you have this, it is typically a desexcitation, almost instantaneous, and it could appear during the measurement process. And you don't know when it appears. How to take this into account? In this case, psi, the wave function, has to be replaced by rho, the density operator. You cannot escape to use rho in this case. This is not possible. And rho will obey, instead of this simple, I will say, quantum trajectory, it will obey also to another quantum trajectory by rho, which is called a stochastic master equation. Cool. I will detail these two things, just this. What are the model behind this? Okay? And once again, we will go back to the photon box. Look, in the photon box, you remember this. You have the initial state, the state just before the detection. It is this guy. It is spread over G and E with the measurement operator here. And my quantum trajectory, it was just this. The change of psi, okay, depends on, in fact, the measurement outcome. Okay. And now, what is a continuous time quantum trajectory? In this case, you see you have a jump. But you want to have an evolution of psi which is continuous, but maybe not differentiable. Typically, it will obey an Ito process, a stochastic differential equation driven by a Wiener process. How to have this directly here? So what is Y? Y is just the information you get during the time delta t. If delta t is small, the information you get should be small. So which means that the measurement, in fact, the measurement outcome, yk, which is G or E in the photon box, should be replaced by the amount of signal that you get during t and t plus dt. And it should be a small number. But it will be a continuous number, which means it will be a real number. So I replace in my formula y of k by dy of t, which will be a small increment. And typically for superconducting qubit, it will be homodyne detection. It will be, in fact, a small increment in the voltage or in the current of my detector. My current is continuous, but it is not differentiable. It is corrupted by noise. But it is a continuous signal. So it is this. And then what I know that my measurement operator, which depends on yk, it will depend on dy. And the formula, it is this. It should be, since it is continuous, it should be an operator which is close to identity when the time dt is very small. So it is identity plus something. Here, when you recognize the coherent evolution, here this is, in fact, a dissipation due to the measurement process attached to any operator L. And here is, in fact, the fact that your measurement operator depends on the measurement outcome, exactly like here. The measurement operator depends on y. Okay? You use this, and then the measurement back action is just you take this operator, you apply psi, you normalize, and you apply psi at time t plus dt. dt is very small. And now what you need is to have what is the probability law. So look, the probability law, physically, it is a quadratic function of psi. So it should be a quadratic function of psi. So what you have is this. The probability law, in this case, it will be a Gaussian. Okay? This is the Gaussian, okay, of variance dt. Okay? But it is not exactly 1. Here it is 1 plus something. And this thing is exactly the normalization here, up to this global scaling that you can put on M here and here. It's not a problem. And when you consider this probability law for dy, when you develop with respect to dt, a small number, okay, and you neglect order strictly greater than order 1 with respect to dt, you obtain dy. It is this thing, okay? It is dt times something depending on psi plus dw, where dw is a Wiener process. A Wiener process is just a Gaussian, okay, of zero mean and standard deviation, the square root of dt or the variance dt. And with this, you can do, of course, simulation. So I have done for you a small MATLAB simulation, and maybe I will stop here. It is this. So look. It is for the measurement, diffusive measurement, so homodyne measurement of the energy of a qubit. So you see, I define the operator here. And here it is the simulation loop. Okay? So it is very easy to understand that this is the measurement time. Okay? This is my discretization time here. This is the initial state. It is G plus E over a square root of 2. This is just buffer for graphics. And here what I do in my simulation, it is quantum Monte Carlo simulation. I use a random generator, but with a Gaussian law. I compute dy, like this. I compute m of dy, and I update the wave function, and I do the loop with this. And what we obtain is this. So it is interesting to see what's going on in the continuous time. It is this. So I measure sigma z. And you see I start from z is equal to 0 in this case. So you see the evolution. So it is one stochastic evolution. And here it is the integral of dy. Okay? Y is your photocurrent, your current in the homodyne detection. And dy is the small increment between the two time steps, infinitesimal time step. And you see that you converge to z because the slope, average slope of your detection is positive. Okay? If you do another realization, maybe you have another trajectory, but it will always converge to z is equal plus 1. So I will do another one because I need to converge. Yes, in this case, you see, I converge to, in fact, the other one. And I recover, I see that after a certain time since the slope of my measurement is negative. So it's the way that you measure in a very efficient way the energy of a qubit. Because the measurement time here could be, I don't know, Zaki, maybe. Measurement time for a qubit, one microsecond? Huh? Hundreds of nanoseconds to do that. Voilà. No. So you will have this small MATLAB simulation. It's a very basic thing. And I will finish by Y density operator, and then I will stop because it is 6 o'clock. So Y density operator. Go back to the photon box once again. Assume that. So this is my basic model on the photon box. Okay. And assume that my detector. I send the atom, but my detector is out of order, which means that I have 0. I have an empty signal. I have to do something because the atom has interact with a photon, but I don't know what is the measurement of the atom. The only thing what I can do is to do some average prediction. But to do average, you cannot average unitary vector because you are not on a convex space. The only way to average things is to use the orthogonal projection associated to a wave function and to average this orthogonal projector. And in this case, what you do is just you do what is the expectation value of psi1 knowing only psi0. I don't know what is y. And what I do is just I take the orthogonal projector of this thing on this unitary vector times the probability plus the orthogonal projector on this unitary vector times probability. But in this case, you see, the orthogonal projector, it is this ket time, in fact, the bra. So the square root disappears, and you see that you recover exactly the probability law. So which means that in expectation, the orthogonal projector on psi1, okay, in expectation, knowing psi0, it is a linear map with respect to the orthogonal projector on psi0, which means that it is typically what is called in quantum information this a quantum channel. So you have ρ, which is in fact in the convex space of Hermitian non-negative operator of trace 1. And you have, in this case, without any detection, you still have an action. Your measurement, your atom has interact with a photon. Okay? Another will interact, and this will change you, not the wave function, but it is not, but just the density operator. It is the average evolution in this case. Okay. And now assume that my detection efficiency is not 0. Okay, you agree. Detection efficiency 0, it means that the detector is out of order. Okay, because it gives you nothing. So in this case, you have a detection efficiency which is between 0 and 1. So either you detect something, or you detect nothing. So in this case, you have three possibilities. Either you use this thing, or you use this thing with eta to take into account the detection efficiency, or you take 1 minus eta, these two things. Okay? And it's the way you construct the density operator that follow the number of photons. It is exactly plus some error, measurement error, and so on. Here it is just detection efficiency. You can complexify this, but it is the way that, in fact, with the density operator, you follow, in fact, the quantum state of your system. Quantum state of your system is just the information that you have on your system, depending on the initial position and the measurement that you have done on your system, and the model that you have used. Okay. So I think I will pass all these things, so you can do this. Too much. So, and what is the analog of this? Maybe you have this. You see, for the photon box, so you see I have some partial mixture here. Okay, like this. If you do that in continuous time, so this is something which is quite ugly. This is a stochastic differential equation. So for mathematician, it is nice, but I guess that for physicists, it is quite ugly. But this thing is nothing but this thing, which is much more interesting from a physical point of view, because here, eta is the detection efficiency. Okay? When m, it is this thing. So you have a unitary evolution that you recognize the Eurouville equation here. Here, what is called, it is called the Lindblad dissipative term. Okay? And here, with dw, it is the measurement back action, where dw is linked to dy by this. And if you write down this stochastic differential equation with the Ito rules, okay, you can write it like this. It is a very good exercise using the Ito rules, okay, stochastic differential computation, to show that rho of t plus dt is equal to this thing. And what is d rho of t? It is just rho of t plus dt minus rho of t. This thing or this thing is completely equivalent things. But for numerical scheme, it is much more attractive to use this formula than this one, because you preserve positivity automatically here. Okay. Well, and now I will put, because my background is mostly mathematical control theory, so I have to do some feedback scheme at the end, but putting some quantum stuff inside. So quantum error correction in the diffusive case. So what you have, so you have your big Hilbert space involving different large number of qubits. The density operator is rho. And you see you have two things here. You have, maybe it's a little bit difficult to read this. You have decoherence, dissipation. It is due to the fact that the error occurs. The errors, they occur, and you don't measure them. So it is as if you have zero detection efficiency on the error. So you have just the Lindblad terms. And you add, of course, in fact, the measurement syndrome. So you have both in this case. So you need to represent quantum error correction in the diffusive case. You need stochastic master equation with the density operator. You cannot escape from that. You cannot just concentrate on the wave function. It's not possible. And the problem, so the dy, you get some partial information on your system through the measurement syndrome. LM will be your measurement syndrome. Okay? And you do what is the correcting algorithm. In the previous case, it's just I measure something in the discrete case. And when I measure something, I know where I am. and I do a pulse like this. Now I know after a certain time where I am, but not instantaneously. And I have to do not a pulse, but something which is also continuous. Not so simple. OK? Well. So what kind of classical controller we can put here? So this problem, in a certain sense, the first paper that investigate this issue was a paper of Andrew Doherty, an Australian physicist, and a nice paper. But it is, they don't prove some convergence results and also precise estimate of convergence rate and so on in closed loop. So, and we are working on this thing. Last point. So it was continuous time quantum error correction. And you have also another point, and I will finish by this. It is autonomous quantum error correction. So and this idea go back to Kastler with optical pumping. So maybe you know what is optical pumping. So it is this. You have a three-level system. And here you have, people say, a largely unstable state. OK? And here you have two ground state. And you want to prepare, so you are in a thermal environment, and you want to prepare only this state. So I have G1, I have G2, and here I have a state which is highly unstable, FF. Okay? And what I do is when I am in the state F, either I relax by dissipation process. Lindblad operator L, in this case, it sends you F to G. So it is this thing in this case. With this. Here you have a dissipation process, the same thing. So it is G2, it is F. So here you have typically gamma 1 and gamma 2, it is the rate of dissipation between the two. And you want, in fact, to go there. All what you have to do, since you have I will say, you need some separation of things, or some separation, you put a drive only on this transition, which is a coherent drive, which means that you have something where a control U, which is constant, it is G1 F plus F G1. Okay? You have both things. Here I have only the disexcitation, but I have also excitation and disexcitation, coherent absorption and emission of photon. So in this case, what's going on? So it's going on, you tend to go there. When you are here, you have a probability to go there or there. Okay? If you continue just in continuous time, if you light on this transition here, you always finished here. Okay? So you exploit a dissipative process, but you put some energy into your system to achieve, in fact, the preparation of this thing. It is called optical pumping. And if, in fact, this idea of autonomous correction go back to, in fact, optical pumping to Kastler, and it is called after that population coherent trapping, dissipation engineering, autonomous feedback, and so on. And here you have a famous guy, Wolf, Zoller, Sirac, and Lloyd, that are using this thing. Okay. And what is behind this idea? So if you put this in a big scheme, so your system is this one. It has small error with I will take a small decoherence time scale, a slow one here. Okay, it is very weak here. But you want to correct this. What you have to do, you have to couple to this system another system, but I will say it is, at least for me, a quantum controller with a much stronger dissipation. Okay? To evacuate, in a certain sense, the entropy of the system. Okay, you have this. And this could be seen with what is called coherent feedback. Your controller is a quantum system, in a certain sense, highly dissipative and well coupled to your goal system. And additionally to that, so you can also use some measurement apparatus, typically on the quantum controller, okay, to get some classical information, because at the end, in each experiment, you need some information to check what you are doing at the end. You need that. So you always have this channel, in fact, of measurement. And you can do typically still, in fact, a correction with a classical controller. And it is clear that this remote control here, it's quite close, so it should, in fact, control fastest time scale. And this classical controller in this scheme can only control the slowest one. But here, in a classical controller, you can put more versatile algorithm, because it is a digital one, so you have much more flexibility than here, because here you are completely under the constraint, physical constraint, when you have a qubit, okay? You cannot take any interaction operator and any dissipation. You are limited by, in fact, the experimental constraint. Here, in a certain sense, once dy is here, you can put almost everything here. So you have to perform a good trade-off between these two things. Okay. Voilà. And that's it. Thank you.
So I was just wondering for the just to make things clear on the 9-qubit Shor's correction. I was a bit confused because you said it's correcting bit flips and phase flips,
yeah.
And you said you need to correct at least 3, or let's say when you correct 3 kinds of errors, you correct all of them. So, but is it then working or not? Is it correcting for any kind of single qubit errors?
Yes. Yes, because of this. Yes. So when, in this case, you need this, of course. You need to check that when one qubit is undergo X, Y, or Z jump, it goes to different plane, and for the 9-qubit, all these planes should be orthogonal. This is the key issue. But now, assume that I have an arbitrary error on my qubit. For example, sigma minus. Sigma minus, I can say that it is a linear combination with complex coefficient, if I want, of identity X, Y, and Z. So the effect of sigma minus, it is I take my error operator here, and here you see I take the value of my error operator of Psi, and then I normalized, which means that I have this. So I will make another time the figure. So here I have the code space. Okay? And here I have for X, okay, I have this one. Here I have this one. And here I have this one. So initially, my wave function is only on these things. And then I take psi, and I obtain what? I obtain I psi plus B X psi plus C Y psi plus D Z psi. Okay? Which means it is spread among these three things. And then I do a Q&A measurement, but on the blocks. So when I do my measurement, I will converge to one of the blocks where I have some support, when one of the guy is not 0, because the probability will be 0. So the measurement process, in fact, do the collapse of the wave packet on one of these guys. And it tells me which packet, which plane it is. And then I can correct.
Preserving alpha.
And yes, I think. It's a way, it's working. But of course, in a 9-qubit space, I do not show you what are the syndromes. You can imagine the syndrome is not so easy to explain. You can find them in the... This is the way where they use some stabilizer code to express in a compact way the syndrome. Yes?
Excuse me. Okay. The point I didn't understand is that when you do your syndrome measurement, it's a projective measurement. So do you have to do it several times? No,
just one. So the syndrome, you have different operator that gives you some partial information. Typically, you can imagine that the first operator tells you, okay, which qubit has jumped. And then you will another operator that will tell you, in fact, which jump has occurred, okay? Typically, when you see this here, in this case, you see? I use, in fact, 3 syndrome measurements, but all these measurements are commuting observable. So it is as if I have a big one, okay? Okay, I have one eigenvalue corresponding to this, another one corresponding to this eigenspace, a different one to this eigenspace, and so on. But this is the eigenspace. So when you are inside the eigenspace, the wave function is not touched. That's the key. So the measurement operator, the syndrome, they are degenerate spectra, of course. Eigenvalue have a multiplicity at least of 2.
But after the syndrome measurement,
yes?
Like the wave,
just a global function.
Just
a global minus in front of it.
Okay, like you don't change the wave function, in fact, by doing the syndrome measurement.
No.
It's not projective. That's the thing. For me,
it's projective by block.
Okay.
But inside the block, I don't touch. Alpha and beta. That's the trick.
Yeah, then let's thank